4.5, an algorithm for curve sketching. So we're going to bring this all together. The reason why we spend so much time analyzing graphs and graphing them by hand instead of using graphing software is so that we can develop an understanding of the qualitative features of the functions we're analyzing. So also, many max, min, and inflection points are not obvious in graphing software. Okay, so here's your algorithm for sketching a graph of y equals f at x. Okay, so we're focusing on two different graphs. We're first focusing on the polynomial function, and then we're also focusing on the rational function. So number one, what we want to do is determine any discontinuities or limitations on the domain. Okay, for discontinuities, investigate the function's values on either side of the discontinuity. Okay, then we're going to determine any vertical asymptotes, determine any intercepts. Okay, so that's x-intercept and y-intercept. Okay, and then we get to the calculus portion of this, of graphing. Okay, we're going to determine any critical numbers by finding where the derivative equals 0 or where the derivative is undefined. Both of these are going to be critical numbers. Okay, determine the intervals of increase and decrease, and then test the critical points to see whether they are local max, min, or neither. Okay, that's going to be the chart for f prime at x, right? Increase and decrease, we're talking about the slope. Is the slope positive or is the slope negative? Okay, then we're going to determine the behavior of the function for large positive and large negative values of x, which will identify any horizontal asymptotes. Okay, identify if the function's values approach the horizontal asymptote from above or below. Okay, again, that's going to be a chart. And just remember, any vertical asymptotes and horizontal asymptotes are only going to be in the rational function. So you can say rational only. Okay, and for this one, we can say rational only. These do not exist in a polynomial. Okay, then we're going to determine the second derivative, okay, and test points of inflection using intervals of concavity. Remember, we equate that to 0, and then we test. Because unless it goes from concave up to concave down, if it goes up, up, it's not a point of inflection. It needs to go from up to down or down to up. Okay, we'll determine any oblique asymptotes. These two kind of go hand in hand, okay, and identify if the graph approaches the oblique asymptote from above or below. And then we're going to go ahead and sketch. Okay, example 1, use the algorithm for curve sketching to sketch the graph of f at x equals negative 3x cubed minus 2x squared plus 5x. Okay, so number 1 is determine the domain. So the domain of this one is going to be XER, simply because it's a polynomial. Okay, there's going to be no restrictions. Okay, number 2, no vertical asymptotes. We're going to find the intercepts. So first, let's find the x-intercepts. We have f at x equals negative 3x cubed minus 2x squared plus 5x. Okay, we're going to do this by subbing in y equals 0 or f at x equals 0. Okay, so we get 0 equals negative 3x cubed minus 2x squared plus 5x. So what we want to do first is pull out this x. Actually, we can pull out a negative x. Okay, we're left with 3x squared plus 2x minus 5. So what two numbers multiply to negative 15 and add to 2? So we get 1, 15, 3, and 5. So 3 and 5 are going to add to negative 2 and multiply to negative 15 as long as the 3 is negative. Okay, so let's do factor by decomposition. So we have 3x squared, and we're going to break down this 2x into minus 3x plus 5x then bring down this negative 5. Okay, we're going to factor by grouping. We're going to group the first two terms and the last two terms. So 3x, I can pull out of 3x squared minus 3x, and we're left with x minus 1. Then I can pull out a 5, and we're left with x minus 1. Okay, these two should be identical. So our fully factored form of this function is negative x, 3x plus 5, and x minus 1. Okay, so our x-intercepts are 0, comma, negative 5 over 3, comma 1. Okay? Now, for the y-intercept, we want to sub in x equals 0. So we take our function, f at 0 equals, we sub in negative 3 times 0 cubed minus 2 times 0 squared plus 5 times 0, and we get 0. Okay, so f at 0 equals 0. That's going to be our y-intercept. Please remember, if we have an x-intercept of 0, we also have a y-intercept of 0. Those two go hand in hand. Okay, so if we come up here and we start to graph this, we can graph our intercepts. Here's our 0, okay, and that's both our x and our y-intercept of 0. Negative 5 over 3 and 1. So negative 5 over 3 is going to be here, and 1 is going to be here. Okay, that's what we know so far. Okay, so we're done with the original. Now let's move on to the first derivative. So we're going to find the critical points. In order to do that, we have to find f prime at x, and I get negative 9x squared minus 4x plus 5. And we want to set this equal to 0. So 0 equals negative 9x squared minus 4x plus 5. Okay, so first I'm just going to pull out a negative so that the leading coefficient's positive. And then we're going to factor by grouping. So what two numbers multiply to negative 45 and add to 4? So the factors of 45 are 1 and 45, 3 and 15, and 4 and 9. Okay, so we would add to 4 if, or sorry, 5 and 9. We'd add to 4 if this was a negative on the 5. So let's break down this middle term into negative 5x plus 9x. Okay, and we'll do that right here. 0 equals negative. Okay, we have 9x squared. We're going to break down that 4x into 9x minus 5x, and then carry up that negative 5. Okay, now we're going to do factor by grouping. We're going to factor out a 9x from the first two terms. We're left with x plus 1. And we're going to factor out a negative 5 from the other two terms. We're left with x plus 1. Okay, so our fully factored form is negative 9x minus 5, x plus 1. Okay, which makes our critical points at 5 over 9 and negative 1. Okay, so tied in with the critical points, which is step number 4, we have to do step number 5. So I'm just going to do it here so we can see it all on the board. We want to find the intervals of increasing and decreasing. So that's our chart. Okay, so our intervals are going to be right, from negative infinity to negative 1. And then negative 1 to 5 over 9, and then 5 over 9 to infinity. Okay, so going down here, this is going to be our f prime at x. So we can break down f prime at x into these three terms. So negative 1, which is this one, okay, 9x minus 5, and then x plus 1. And then that's going to be our total. So choose a number between negative infinity and negative 1. Let's go negative 10. Okay. Choose a number between -1 and 5/9. Let's choose 0. And 5/9 and infinity, let's choose 10. Okay, so -1 is going to start all of these with a negative. Okay, there's no x value here, so you can't sub in. Now, if we subbed in -10 to 9, so -90 minus 5 is going to be negative. 0 minus 5 is negative. 10 times 9 is 90 minus 5. That's going to be positive. Okay, now -10 plus 1 is negative. 0 plus 1 is positive. 10 plus 1 is positive. So in total, this is going to be increasing. Sorry, this is going to be decreasing. I put a negative. There we go. Negative is decreasing. Overall sign here is positive, so it's increasing. And then overall sign here is negative, so this is decreasing. Okay, just to add one more thing to the critical points, we can go ahead and sub in f at 5/9 and f at -1 to get where the actual points occur. So we want to sub these into the original. So when we sub in 5/9, we get like 400 over 243, which is just, let's just round to 1.6. Okay, and then when we sub in f at -1 to the original, we get -4. So now let's go ahead and go up to our graph and sub these in, okay? So we have 5/9 and 1/6. And if you think about what 5/9 is, when you divide that, it's 0.55. So 0.55 and 1.6 is going to be a point. Okay, and then we have -1, -4. So -1 is going to be here, -4 will be down here somewhere. Okay, so that will be that point. And then we can also say, so we're decreasing from -infinity to -1. Okay, so -infinity is over here. So we're decreasing to -1, which is here. Then we're increasing between -1 and 5/9. Okay, so -1. So increasing, yep. And then between 5/9 and infinity, we're going to be decreasing again. Okay, so this is infinity. We're going to be decreasing again. Okay, and this is our f at x. We're not done though. We still have to continue the algorithm, even though a lot of this graph is completely done. The next points, when we test points of inflection and concave up and concave down, it should reinforce what we have here. Okay, so the next step is step 6. Oh, one more thing for this. Because we go from decreasing into increasing, we can actually label this. So this point at -1, so we're going from decreasing to increasing, this is going to be a min. And because we go from increasing to decreasing, this point is going to be a max. Okay, we're going to have a max at 5/9. So let's actually label those. So max value of 1.6 at 5/9, and we're going to have a min value of -4 at -1. Or we can put x equals -1 and x equals 5.9 or 5/9. Okay, we can also explicitly label the intervals of increase. Okay, so we increase and then decrease. We increase on -1 to 5/9, not including these numbers, because at those numbers we stop, and then decrease on -infinity to 1 and 5/9 to infinity. All right, so now let's do number 6. Okay, there's no horizontal asymptotes. Okay, number 7. Determine the second derivative and test for points of inflection. So we're going to first start with the second derivative, f double prime, and I get negative 18x minus 4. And let's solve for when that equals 0. Okay, so bring over that negative 18x, it becomes positive 18x equals negative 4. And let's go ahead and divide both sides. So we get x equals negative 2 over 9. Okay, so there's a possible point of inflection. So let's go possible point of inflection at negative 2 over 9. And if we want to know where negative 2 over 9 actually lies in the graph, we sub this into the original and we get negative 35.1 approximately. Okay, so now let's actually test the points of inflection. So we're going to start with the interval here. Okay, we simply have a linear function. So let's just go negative 18x minus 4. Okay, which is our f double prime. So this is our f double prime at x sine. Okay, and we have negative infinity to negative 2 over 9. And then we have negative 2 over 9 to infinity. Oh, let's put x equals negative 2 over 9 in the middle because we're going to test that point of inflection, and then negative 2 over 9 to infinity. Okay, so choose a number between negative infinity and negative 2.9. Let's just say negative 10. Okay, so this is going to end up being positive. Okay, so for our concavity, for positive, is going to be concave up, which looks like this. Okay, if we subbed in negative 2 over 9, we get 0. So let's have this pending for a second. And then if we sub in a number between negative 2 over 9 and infinity, let's just say 0, we're going to get negative. Okay, so that's going to be concave down. And because we go from concave up to concave down, this is indeed a point of inflection. Sorry, this is negative 1.2. That looks better. Okay, so now that we have concavity, I'm just going to finish number 8. Okay, there's no oblique asymptotes. Okay, and number 9 is our sketch. So let's go back up here to the concave up and concave down. Okay, so on our graph, let's label the point of inflection 2 over 9, comma, negative 1.2. So negative 2 over 9 is about here. And this is going to be our negative 1.2. So this is going to be our point of inflection. And then if we look at our concavity from negative infinity to that negative 2.9 is concave up, and that's what we have. And negative 2.9 to infinity is going to be concave down. So then this interval is going to be concave down. Okay, sketch the graph of f at x equals x minus 4 over x squared minus x minus 2. Okay, so number 1, what we're going to do is we are going to see the domain. So first of all, we need to factor the denominator here. So go ahead and leave the numerator since it's a binomial. And what two numbers multiply to negative 2 and add to negative 1? Okay, well, it's going to be 2 and 1, and the negative is going to be on the 2. So in the denominator, we have x minus 2, x plus 1. Okay, so what this means is that whenever the denominator equals 0, we're going to have vertical asymptotes. So we have vertical asymptotes at x equals 2 and x equals negative 1. Okay, so that means our domain is XER such that x does not equal 2 or negative 1. Okay, and if we want, we can go to the side of our paper and we can start graphing this. So we're going to have a vertical asymptote at 2 and a vertical asymptote at -1. Okay, now number 2, find the intercepts. So we're going to find the x-intercepts first, okay, and then that's when y equals 0. So the x-intercepts are when the domain equals 0, okay, because if we had 0 equals x minus 4 over x minus 2 x plus 1, and we cross multiplied these two terms up to the 0, we're still going to have 0 equals x minus 4, which is just the numerator. Okay, so our x-intercept is occurs at 4. Okay, and now our y-intercept, come up here, is when f at x, oh sorry, when we sub in f at 0. Okay. I'm going to put it like this. So we have f at 0 equals 0 minus 4 over, I'm going to use this one, 0 minus 2, 0 plus 1. So in other words, it's going to be -4 over -2 times 1, which is -4 over -2, which is just 2. So our y-intercept is 2. So let's go ahead and plot those on our graph. Okay, we have an x-intercept at 4 and a y-intercept at 2. There for now. Okay, we might have to move those up or down depending on our scale. Okay, so we're done everything with the original function. Now let's move to the first derivative. Okay, so that was number 3. Intercepts were number 3. Oh, number 2 was the vertical asymptotes. So what we're going to do is determine any critical numbers. Okay, actually number 3, we're going to go back up to number 2 and do the vertical asymptote chart. Okay, so here is our vertical asymptote chart, VA chart. Okay, and this is an extension of number 2. So we can call this VA. The 3 parts of our equation is x minus 4, x minus 2, and x plus 1. Then we're going to get some sign, and then we're going to be able to determine if where f at x approaches. Okay, so we're going to first do when x approaches -1 from the left, then we'll do -1 from the right. Then we'll do as x approaches 2 from the left and as x approaches 2 from the right. Okay. Now, what number can we sub in? For -1 on the left, we're going to do -1.1. Okay. Negative minus any negative is negative. Negative minus any negative is negative. -1.1 plus 1 is going to be negative as well. So the overall sign is negative. So as x approaches -1 from the left, we're going to approach -infinity. Okay, now let's do -1 from the right. I'm going to get -0.9. Negative minus a negative is negative. Negative minus a negative again is a negative. -0.9 plus 1 is going to be positive. So this sign is actually going to be positive. Oh, I don't have to write that again. Okay, so it's positive infinity. Now, x approaches 2 from the left. Let's plug in 1.9. 1.9 minus 4 is negative. 1.9 minus 2 is negative. 1.9 plus 1 is positive. Therefore, we get positive. So we approach positive infinity. Okay, and as x approaches 2 from the right, we can sub in 2.1. 2.1 minus 4 is negative. 2.1 minus 2 is positive. 2.1 plus anything is positive, so therefore we get negative. So then we approach negative infinity. So now that we're done the vertical asymptote chart, we can go back up to the original and we can sketch where the arrows are. So around -1, we're negative and then positive. So around -1, we're negative on the left and positive on the right. Okay, and then around 2, on the left we're positive and on the right we're negative. Okay, so on the left we're positive and on the right we're negative. All right, now let's do everything having to do with the first derivative. So for number 4, we're going to find critical points. So we're going to take f at x, and it's going to be x minus 4. I'm actually going to bring up this x squared minus x minus 2 and raise it to the -1. So let's find the first derivative. Okay, it's going to be product rule. So the derivative of the first, which is just 1, times the second as it is. Okay, plus the first as it is times the derivative of the second. So bring down the -1, write what's in the bracket, and then what is the derivative of what's in the bracket? 2x minus 1. Okay, so f prime at x equals, I'm going to simplify this, and I'm just going to bring that to the front. So x squared minus x minus 2 to the -1 minus, because that's going to go here, x minus 4. I'm going to put the other binomial here, 2x minus 1. And then we have x squared minus x minus 2 to the -2. So in these two terms, we're going to factor out x squared minus x minus 2, okay, because those are identical. And what we're going to do is we're going to take the lower of the two exponents. So I'm going to factor out a -2. So our common factor is x squared minus x minus 2 to the -2. When we get -1 minus -2, we're left with this term to the 1. Then those cancel and we're left with this. What I'm going to do in this step is I'm going to go ahead and expand this because I know I'm going to need to in the next step. So I get 2x squared minus x minus 8x plus 4. And I'm going to copy down this first factor and just expand this next, like simplify this next bracket. So what is x squared minus 2x squared? It's negative x squared. Negative x plus x, that will go away. So then we have negative 8x. And then minus 2 minus 4 is going to be -6. So let's just pull out this negative sign. So we get negative x squared minus x minus 2 to the -2, bracket x squared plus 8x plus 6. Okay, so we can either write it like that or we can write it as the fraction, like the quotient rule. Okay, so because this is -2 in the exponent, this would now be in the denominator, x squared minus x minus 2. And then this would be in the numerator, okay, x squared plus 8x plus 6. Okay, so for our critical points, we want to know when the derivative equals 0. So let's set this to 0. If we think about any denominator, oh, this is going to be squared in the denominator. If we cross multiply, the denominator doesn't matter. We're just going to equate the numerator to 0. So we want to know when x squared plus 8x plus 6 equals 0. Okay, what two numbers multiply to 6 and add to 8? There is no numbers, so you'd have to use quadratic formula. Okay, this is a -8. So our A value is 1, our B value is -8, and our C value is 6. Okay, so let's go ahead and sub that into the quadratic formula. So I get x equals 8 plus minus square root of -8 squared minus 4, 1, 6, all over 2 times 1. So I get 8 plus minus, I get 2 root 10 over 2. Okay, so these 2's cancel, this goes to a 4, and I get x equals 4 plus or minus root 10. Okay, if we actually put that into our calculator so that we can graph that on the graph, we're going to get 7.1. And 4 minus root 10, we're going to get 0.8. As our critical points. If we were to sub those in, so what is f at 7.1 and what is f at 0.8? We get 0.08 and then we get 1.5. So going back to, let's go ahead and graph those. Going back to the graph, 7.1, comma 0.08. So this will be 7.1, and this will be 0.08. Okay, and then we're going to have 0.8 and 1.5. That'll be 1.5 right there. Okay, so let's take those and let's actually do the chart for the intervals of increasing and decreasing. So we are going to have the interval for f prime at x. Okay, so this is going to be the chart for increasing and decreasing. Okay, and we're going to start at -infinity, and we're going to include two things. We're going to include our critical points, and we're going to include our vertical asymptotes. Okay, so let's list all of them. So all of the points that we're going to use, so critical points and vertical asymptotes. Our vertical asymptotes are 2 and -1, and our critical points are 0.8 and 7.1. So 0.8 and 7.1. Okay, so we're going to start at -infinity, and then we're going to go to -1, and then -1 to 0.8, 0.8 to 2, and then to 7.1, and then to infinity. And from our function, we're going to have -1, and then our numerator is going to be x squared minus 8x minus 6. And then our denominator is x squared minus x minus 2, and then that's squared. Okay, so this is not as taxing as it looks. Everything with the -1 is going to be negative because there's no variable there, so it's never going to change. Now our denominator is squared. Any number squared is going to yield a positive number. So we're going to base this solely on this bracket, x squared minus 8x minus 6. So let's plug in a number between -infinity and -1. Let's do -10. And we're going to get 100 plus 80 minus 6 is going to be positive. So this is going to be negative, which is decreasing. A number between -1 and 0.8 is 0. So 0, 0, -6 is negative, so this is positive, so it's increasing. And a number between 0.8 and 2 is 1. So 1 squared minus 8 is -7. Minus 6 is still going to be negative. So this is going to be positive, which is increasing. Okay, sorry, there's going to be plus 6. Okay, so for -1, there's no variable. All of these are going to be negative. Okay, so and for any number squared, all of these are going to be positive. So let's plug in numbers between negative infinity and negative 1. Let's go negative 10. So we get 100 plus 80, that's going to be positive. So this is negative, which is decreasing. A number between negative 1 and 0.8 is 0. So 0, 0 plus 6, this is going to be negative, so this is decreasing. A number between 0.8 and 2 is 1. So this is 1 minus 8, which is negative 7, minus 6, which is negative. So this is positive, which is increasing. A number between 2 and 7, which is 4, let's say. Okay, so 4 squared, which is 16, minus 8 times 4 plus 6. We're going to get a negative. So this is positive, which is increasing. And let's just say 10. That's 100 minus 80 plus 6, which is going to be a positive number. So this is negative, which is decreasing. Okay, so going from decreasing to increasing, this is going to be a min, and it's going to occur at 0.8. Okay, and going from increasing to decreasing, this is going to be a max, and that's going to occur at 7.2. Okay, and intervals of increase are going to be 0.8 to 2 and 2 to 7.1. And the intervals of decrease are going to be negative infinity to 1, negative 1 to 0.8. Oops, that's negative. And then 7.1 to infinity. So let's go ahead and graph that. So increase point, let's start with decrease. Decrease on negative infinity to negative 1. Okay, so negative infinity to negative 1, we're decreasing this whole time. Okay, we still don't know if we approach the horizontal asymptote from above or below. Okay, and then we're going to decrease and then increase. And then we are increasing again. And then decreasing. So, and again, we don't know, so this is infinity, we don't know if we're going to approach from above or below. So we're going to leave that for a second. Okay, let's move on to number 6. So that's determine the horizontal asymptotes and the end functions, okay? So 6 looks like this. Okay, so horizontal asymptote is going to be, so we have x to the 1 over x squared is going to be x equals 0. Sorry, y equals 0, that horizontal line. Okay, so now what we want to do is we want to see the limit as x approaches negative infinity of x minus 4 over x squared minus x minus 2. Okay, so let's go ahead and factor out an x out of the numerator. So we get x bracket 1 minus 4 over x. And in the denominator, we're going to get, let's factor out an x squared. And we're going to get 1 minus 1 over x minus 2 over x squared. Okay, so this x and this squared cancel out. When we actually, let me write limit as x approaches negative infinity. When we actually sub in negative infinity, we get 1 over 4 over negative infinity, which tends to 0. Okay, and then we get negative infinity bracket 1 minus 1 over negative infinity, which tends to 0, minus 2 over negative infinity squared, which tends to 0. Okay, so 1 over negative infinity is going to tend to 0. So that's checking the horizontal asymptote. Okay, the other check is let's ensure that it's a horizontal asymptote by checking when x approaches infinity. So I'm going to use this one here. Okay, so because we already did that legwork. So, I'm going to leave x for now. So we're still dealing with 1 minus 4 over x, 1 minus 1 over x, minus 2 over x squared. Okay, and now let's go ahead and sub in. We get 1 minus 4 over infinity, which tends to 0, over infinity, 1 minus 1 over infinity, which tends to 0, minus 2 over infinity squared, which tends to 0. So we essentially get 1 over infinity, which is 0. So our check for the horizontal asymptote, okay, is approved. Therefore, y equals 0 is a horizontal asymptote. Now what we want to do is we want to plug these into the chart. Okay, we want to see as x approaches, okay, and we're going to do infinity and negative infinity. Okay, what's happening with f at x? Well, we can sub in f at 100, and we can sub in f at negative, 1000. Let's go 1000. And we get 0.0009, and we get negative 0.001. Okay, so where does this approach? So this is going to approach from above because we're comparing this to y equals 0. So this is a bigger number, so above. And negative anything is going to be below. So let's graph this. So as we approach infinity, we're above, negative infinity is below. Infinity, we're approaching from above, negative infinity, we're approaching from below. Okay, so that solidifies that part of our graph. Okay, now let's focus on 7. Let's find the second derivative. So the first derivative was negative x squared plus 8x minus 6 over x squared minus x minus 2 squared. So that means our second derivative, let's pull this up and use the product rule. Okay, so derivative of the first is going to be negative 2x plus 8 times the second as it is. That's going to be x squared minus x minus 2 to the negative 2, right? Because if we pull this up, plus the first as it is, okay, times the derivative of the second. So we are going to get, if we bring this, it's going to be negative 2. If we bring the negative 2 in front, the bracket as it is, so x squared minus x minus 2 to the negative 3. And then the derivative of the inside, which is 2x minus 1. Okay, so now we have to work with that in order to fully factor and then set equal to 0. Okay, so I'm going to leave the first two terms as they are. So negative 2, you know what? I'm going to pull out a negative 2. Negative 2, and we have x minus 4. Then we have x squared minus x minus 2 to the negative 2. Okay, so we have negative 2 again in front. I'm going to put the binomial 2x minus 1, and then I'm going to put this trinomial. Oh, see how there's a negative? I'm going to factor that out. So that's going to go to plus, and we're going to have x squared minus 8x plus 6. And then I'm going to have x squared minus x minus 2 to the negative 3. Okay, the common term here is going to be x squared minus x minus 2. Okay, x squared minus x minus 2. We're going to take the lower of the two exponents, which is negative 3. So f double prime at x equals, our common factor is x squared minus x minus 2 to the negative 3. Then we have these two terms left over. I'm actually going to distribute those back in. So negative 2x plus 8. Now we have, so this one goes away. Oh, for the first one, we also have x squared minus x minus 2 left over because negative 2 minus negative 3 for exponent loss gives us one of these in the numerator. Okay, and then plus this is left over in the second term. So I'm going to go ahead and distribute this in. So we get 4x minus 2. And then I'm going to rewrite this, x squared minus 8x plus 6. Okay, so I'm going to write the first factor as it is and leave that there. And now I'm going to FOIL these two terms, completely expand. So negative 2x times x squared is negative 2x cubed. Negative 2x times negative x is positive 2x squared. Negative 2x times negative 2 is positive 4x. Now, 8 times x squared is 8x squared. 8 times negative x is negative 8x. And 8 times negative 2 is negative 16. Okay, now 4x times x squared is 4x cubed. 4x times negative 8 is negative 32x squared. Okay, 4x times 6 is going to be positive 24x. Now negative 2 times x squared, scroll all the way over, is going to be negative 2x squared. Negative 2 times negative 8 is going to be positive 16x. Negative 2 times 6 is going to be negative 12. Okay, so in the next line, I'm going to write the first factor, and then I'm going to collect all my like terms. Okay, so I have 4x cubed and negative 2x cubed, so I have 2x cubed, 2x squared, 8x squared, so that's 10x squared, minus 32x squared, minus 2x squared. I get negative 24x squared. I get 4x minus 8x plus 24 plus 16. So that's 36x. I get negative 16 and negative 12. I should get negative 28. Okay, so let's rewrite this. I'm going to factor out a 2 out of that second bracket. We're left with x cubed minus 12x squared plus 18x minus 14. And I'm going to move this x squared minus x minus 2 to the denominator. So when taking a look at the second derivative, okay, this, when we put it into like a graphing software or a calculator online, we cannot factor this. Okay, so cannot factor. So we just interpret this to be like we have enough information to graph our equation, and I just want to point out there's no oblique asymptote. Okay, so going back to this graph up here, this is going to be what our f of x looks like.